But first and foremost, it's my first trip into Europe from the data center spectrum. I've been in the industry for 30 years, built 10 different data centers for ourselves, built a bunch of data center projects for customers. But first time here in the European stage, so I figured I'd talk a little bit about who I am, what we do. Been around the block quite a bit. We have 5 data centers in the U.S. that we constructed under the ScaleMatrix brand. All of those data centers are built and based on our DDC cabinet technology, which I'll talk about today. Show you a little bit about why it's cool. And most importantly, well, I'm going to tell you that our baby is cute, our technology is great. The good part about it, most of the data that I'm going to share with you is all the results of a customer product that just ended. These are their results, so not tainted by my love of what we do as a data center industry. So hopefully in the next 15, 20 minutes, this is what we're going to cover. We'll talk a little bit about our technology and why it's cool and it does great things in the data center space. Talk about TierPoint, who's the customer that recently adopted our platform for their data centers. And we're going to talk about the 3 things that they found from using our technology in their new data center construction and the benefits that they got from it, right? They figured out a way to do high density in a really great way. They figured out to build data center space at a lower cost. And they figured out how to operate data centers from an ongoing perspective at a lower cost than they've done in the past. Hopefully we get a little bit of that information today as we go through this. So 15 years ago, my business partner and I developed a data center platform called DDC, or Dynamic Density Control. Instead of building the data center out as a whole system and trying to cool the entire platform, we flipped it kind of on its head and made the data center a single cabinet, where we're putting cold air down in front of the rack of equipment. The 4-post rack encapsulated inside a closed enclosure. That cold air is consumed, the hot air is brought back up, cooled right inside the cabinet module, and sucked right back down, so that the data center now is truly cabinet level managed. These things can be deployed 1 or 1,000 as a system. They're like Legos. And they just plug into a central chilled water loop, and you bring power to it like it would a normal rack. This takes kind of some of the problems with age-old data center design and solves them by focusing the area where we're cooling in a much smaller area, making it way more efficient. And because of the way our technology works, it makes it able to cool way more density with just air cooling solutions instead of having to bring liquid to the chip or the chassis. This is a mock-up of one of our cabinets. This is an actual cabinet, and this is a cutaway of the system. What's unique about it is that each cabinet has got both a supply and a return fan control system. Both the hot air and the cool air side of the cabinets are sealed like a plenum. So we're only putting cold air down the front end of the cabinet. That air is then heated up across the server, and then another fan is drawing that hot air off and running it across the local heat exchange. Right? That is a very efficient way of dealing with heat inside the data center. It has no impact on the data center area around it. It creates no hot aisle, cold aisle, or hotspot issues. And it allows customers to continue to keep racking equipment just in a normal air-cooled rack, the way we've done for the last 5 decades. But we've achieved a significant amount of thermal density, being able to support 85 kilowatts of server hardware in a single rack with only air cooling. So that was our platform. We designed it for ourselves, and we built 5 data centers across the U.S. based on that platform. And in 2018, we realized it was working so well that we spun the technology and the intellectual property for that platform out into its own company called DDC. And now DDC operates as a technology services company that sells these cabinets on our platforms to other data center operators or enterprise operators that want to run more efficient, variable density data centers without having to go to the complexity of bringing water to the chip or the chassis. Lots of other benefits from the technology. The closed area provides better security, integrated fire suppression at the rack level, so you don't have to worry about those things. By the racks coming fully outfitted with all these capabilities built in, deploying data center space is much quicker, it's much simpler, and you don't have to spend all the money to condition the data center arena itself. It's really just kind of plug and play out what you need. And you don't have to build the entire facility out at once. You simply add cabinets as you require capacity. It's a whole new way of looking at things, which we found to be very efficient. Because the cabinets are completely sealed, because we're able to really precision control the amount of airflow that happens in the front end. There's no particulate, there's no dirt. It's almost like a clean room environment. And because we're only managing this small amount of air, not the entire data center envelope, we're able to control the temperature variation within a couple of degrees all the time, regardless of whether the kW rack rate goes up and down. So all those things matter because in the end, servers that have a clean room type air environment and have less temperature variation from the airflow in the data center last longer. We have less component failures. We've had customer after customer see these benefits over the last 13 years the platform's been deployed. We don't just sell the cabinet technology itself. The cabinets also come with a fully built out DSIM solution. Because we're monitoring temperature in the front, back, rear, top, and bottom of the cabinet, we've got a lot of information about what's happening in the environmental conditions inside the enclosure. All that data is fed back into the DSIM, and we're able to control the amount of water that we draw from the chilled water system, the amount of airflow and fan control that we need to measure the loads dynamically in real time. So as your customer workloads go up and down, the control valves at the top of the cabinet open and close based on the thermal demands. The fans slow down and speed up based on the CFM control settings. We say, hey, we want to have 150 CFM per kilowatt deployed in this rack. You set that in the software and you don't have to worry about it ever again. It automatically manages to your specific set points. So out of the box, it comes with an easy to deploy system, takes care of a lot of the data center functions, and has software to control it all to give you the visibility and the transparency about what's happening at the data center level. When I talk about how much data there is in the system, it's hard to explain it all in one slide, but when you separate a cabinet down into a forward plenum and a reverse heat plenum, the software is actually looking at both sides and managing the amount of airflow, the amount of water flow through that one cabinet so that you have surgical condition about what the temperature set points and environmental set points are. In this particular example, we've got the set point at 63 degrees supply side, very, very cold. You can run that from 60 to 80, whatever you want your IT hardware to run it. The important part is that we're looking at the top of the cabinet and the bottom of the cabinet, those sensors, and making sure that everywhere in that supply side plenum, you're getting the exact same temperature and the exact same amount of CFM, regardless of the server position. And in this example, it's 70 kilowatts in a single rack. Right? We have a less than 1 degree variation between RU1 and RU45. So that level of precision control is great, especially for newer applications and higher end hardware that's supporting things like AI. We have several form factors in this. 45U, you see here is 60U systems. Those are 9 different systems, all super micro, brand new, extremely high velocity fans. And the system is producing anywhere between 7,000 and 12,000 CFM on the front side supply, which is more than enough for any of the current hardware revolutions that are coming out from the various vendors. So we've got a lot of control, very efficient way of managing it. And for 70 kilowatts, we're using only 2,000 watts of power to cool and manage that workload. So the electrical efficiency is very high. The modularity of it, because it's cabinet-based, right, allows us to deploy data center space very rapidly. In today's changing world, customers requiring lots of different densities at their data center deployment. You can take an existing facility like this that was traditionally cooled with grade 4, already had chilled water and power available, take an unused portion of the data hall and simply ship in cabinets, drop them into place, set up your power distribution in a water filler. And these guys were able to deploy several megawatts of power into a very small corner of the data center in under a 2-week time frame. So we're providing great environmental control, speed of delivery, and some really cool future-proofing, being able to support up to 85 kilowatts in one of these enclosures. And by the way, they don't cost very much. All these features and all the things we built are very, very cost-effective from the infrastructure perspective. We're going to show you. So that's a lot about our technology. We're over in stand 13, 18. They've got one of the cabinets running live. You might want to see them and put your hands on them. It's a great thing to set your eyes into. A very different way of doing things. But TierPoint, the case study that we're talking about today, is a very large U.S. data center operator with more than 40 data centers under their management. Right? Hundreds of employees, hundreds of millions in revenue. And this is very much what their data centers look like many of the data centers you'll find out there today. They had a challenge. They had a very, very large customer come to them recently who wanted to deploy 1,500 plus GPUs in a very, very short period of time. They did the math, and they needed about 324 of our racks that they're going to run at about 50 kilowatts per rack. Right? They had a very short time to deploy it. And the total kilowatt load based on the requirement of the customer was 16 megawatts. In none of their facilities were they able to do so quick enough or with the right efficiency levels, and certainly not from a density level. Right? So they came to us and we worked through a couple of options. They, with a very, very large engineering team, both internal and external third parties, they did a fairly exhaustive review of the engineering options at their disposal. And in the end, much like many of us would be, they ended up looking at modifying their existing data center infrastructure to use enhanced containment, both hot and cold, to be able to service this requirement. They looked at rear door heat exchangers as an option. And then finally, they measured our DDC cabinets as a third way of solving for this requirement. We had a lot of people looking at it, a lot of great research that they put into it. I will walk through kind of their results. This was the criteria they used for evaluating which solution was the best for them from a data center operations perspective. Obviously, how much density they could fit, the amount of CFM they could guarantee each customer at the rack level was important, construction for power costs, construction for mechanical costs, how much physical footprint they would require, mechanical and electrical spaces, both in the yard and internal to the building, fire protection as a subset of the cost. And in the end, all of that would boil up into what was the day one delivery cost to build the data center, right? And what was the operating cost ongoing on a regular cadence based on those three solutions? It was, in the end, a landslide victory for us, right? And this is why our company, we raised a ton of money over the last 6 months. We're growing internationally. The cabinets are now produced in 3 different continents that can ship anywhere in the world and plug into almost any data center environment. From a rack density perspective, at 85 kilowatts per rack, all air cooled, we were a clear front runner from that perspective. Airflow and CFM management, because we have a supply fan that's managing air at the front level of that cabinet, we were the only provider out of containment and rear door that can offer them a guaranteed amount of CFM per kilowatt on the supply side of that server. So that's a very, very strict criteria from a performance perspective from the NVIDIA platform that they're deploying. Power construction costs, we all know power is power is power. So in the data center world, there isn't a whole lot of advantage to our system versus another, but there was a pretty even keel across that from that perspective. Mechanical costs, because our system manages airflow and water flow at the cabinet level, things like crack units, additional fire suppression, all those type of things do not have to be installed. And so the mechanical cost of actually building out the data center is significantly less. IT floor space requirements, because we were able to support the customer up at that 80 kilowatt marker, right? The footprint went from tens of thousands of square feet down to a much, much smaller footprint. While that's useful, when they're building that new infrastructure, building less costs less. So it was another point in our favor for what the overall construction cost of the project would be. Mechanical space, we obviously were able to remove the crack units, so we didn't need as much support for those. Electrical space, again, no clear winner. Electrical is electrical, so we're going to do just as much work as we would with any other solution. In the end, because each of our cabinets is fully contained, it has a volatile compound sensor and an integrated fire suppression agent, we didn't have to make any further investment in fire suppression for this large 16 megawatt expansion they were doing in the Pacific Northwest. In the end, our cost, which we'll share with you guys, as well as the ongoing operational costs, we beat all three solutions. And some of the advantages on our side were significant. So as they were evaluating the results from their testing, right, from a high density perspective, we We won the day with 85 kilowatts, right? Scalable density. The cabinets operate just as efficiently at that 5 kilowatt marker as they do at 85, and they're dynamically managed. So regardless of whether the customer workload goes up or down in real time, the system will adjust the water and fan speed so that you're not wasting or stranding any resources in the data center. Dynamic resource allocation based on cabinet level demand. We offer the only system that can very surgically control temperature both at the front and back, right? And from our dynamic response system made it so that we weren't wasting any energy providing cooling or airflow when the racks were idling or not running a specific AI job. So it's a very interesting platform. From the cost to install, we talked about the smaller footprint helped us reduce the overall construction cost. We reduced and eliminated additional fire suppression, air hammers, there were no raised floor requirements, etc. That helped reduce the overall project cost. And the fact that we were able to deploy this in a very, very short period of time, right? It was a 9-month build for 16 megawatts. We already had a substation on site, so that was there. But we had to extend substation power, deploy chillers, and all the rest of the infrastructure. And the cabinets just kind of plugged in, and over like a 4.5-week period, all the cabinets were online with data center floor. From an operating cost perspective, we designed this platform with a completely closed loop system, so no water cost ongoing. And because we were able to lower energy costs and reduce the energy rate, and because we were able to achieve a PUE that's very low from the outset, as opposed to having to wait for the data center to fill up to reach its true PUE potential, we were able to save a lot of money for them on an operating cost perspective as well. Performance from a customer perspective, the folks in the racks actually using the service, is significant. Because we can guarantee the CFM at the front side supply of those servers, server hardware performs better, and the sealed cabinets obviously help from any particulate from things happening in the data center from getting inside, which is now extremely expensive hardware when you're supporting AI infrastructure. So that clean room type environment was valuable to the customer and end user. Right? Because the cabinets are sealed and have biometric access control, physical security is just better than the alternative. And the fact that this is a big one for those both operating and the customer using the platform, because the cabinets are completely sealed, these high-speed GPU deployments that are extremely loud and unpleasant to listen to are attenuated more than 75% on the cabinet itself. So the data center is actually quiet enough for you to have a conversation when you're in there working. So that's a significant kind of human resource benefit for using an enclosed cabinet system. And for operational cost, having 2 fans, both managing with the airflow, helps ensure more heat transfer off the servers in the center. That's a patented DDC type feature. But also running the 2 fans at a lower fan speed reduce energy cost, as opposed to 1 fan revving up to almost 100%. So we manage all those things dynamically to reduce energy costs. And then by being able to put more density in a single rack, the end user was able to shorten their high density cabling runs into a smaller footprint. And the savings of those Mellanox cables and other high density cables for these large scale deployments was enough to pay for their colo bill for a couple of years. So when you're adding all of the benefits up of how you build new data center space for evolving and variable density requirements, there's a lot of benefits to this fully contained cabinet level system. These are a couple of the photos from the project that's just now being deployed. So you end up with the rack itself that comes shipped in 2 parts. Regular rack here with its 4 posts, adjustable for very long, fits any infrastructure in the industry today. The top hat sits on top of it, and this is your supply and your return fans. In the center is a heat exchanger that connects to any local chilled water source, right? And this container here is segregated so that the water comes in and out of that section, and it's sealed so that the water doesn't actually enter the IT environment. So you get all the benefits of liquid cooling without the risk of water being in the cabinet itself. And you're also able, because of the velocity augmentation from the circular motion of the 2 fans, pushing and pulling air from the system, we're able to support the highest density air-cooled loads in the industry today. This particular customer chose to just build panels, drop their power systems right into the cabinets themselves. And that is the extent of the work that has to happen on the data center floor. Still build out all your power, still build out all your chilled water. Once you get to the data center floor, no space requirements for crack units, no space requirements for extra mechanical. You simply plug the cabinets in, wire them up for power, and off you go. A couple of views from inside the cabinet. Again, we're over in stand 13 and 18 if you'd like to come see one of these firsthand. But this is a view looking up into the cabinet on the rear side. Right, so we've got these high velocity vortex fans that suck all the heat off the back of the cabinet, making sure you don't get any heat blow back into the cabinet in these high density operations. And this is the forward side, the front side, supply cabinet. So some of you guys know if you're working on these newer AI deployments, there's as much cabling coming out of the front of the rack now as there is coming out of the back. For traditional air-cooled data centers where you're bringing up air from the floor or even from a supply that's just drifting to the top, really difficult to get the right amount of airflow to the servers that need it. And because when you close this door, you basically have a pressurized plenum with sides, tops, and bottoms around the rack surface area sealed. You can control the differential pressure of that plenum so that it's a perfect balance where you get just enough buildup so that every server gets the right amount of air, even with these extensive amounts of cables that these new AI deployments are required. And in the end, and these are published results, my email is going to be on the end of here. Anybody who sends me a message again, I will send you the actual report itself. But these are published results from a 16 megawatt build that just got completed under the TierPoint brand, where they chose our cabinets as the solution. And in the end, you can see from adding containment to try to support this environment, construction cost itself was $137 million. Again, they had the substation on site, so this is about, about an $8 million per megawatt build cost. So it drops down a bit here for rear door heat exchangers. There's some efficiencies and things that you can get from that platform. The rear doors don't give you the ability to guarantee CFM at the supply side. They certainly don't do as good of a job of evacuating heat off the back of those servers. And they don't include fire suppression or any of the other things that are fully integrated into this true data center level cabinet solution. And in the end, these are customer numbers, not our numbers, right? This was what their construction costs were to be able to build. And so with our solution, $98 million, which was a significant savings. And then because we're able to manage the amount of water flow and fan speed based on loads dynamically, we simply use less energy because we're not wasting or creating any cooling when it's not necessary. So our target PUE is a 1.2. We have, in a variety of deployments, done better than that. But even in a 1.2, right, your PUE cost alone, right, creates a fairly significant annual savings year after year after year. And so if you can deploy day one, saving this much money over traditional build costs, and end up saving on the long term, and still have a platform that can scale and work for customers at 5 kilowatts all the way up to 85 kilowatts without the need to do liquid to chip or liquid to chassis. We believe that this platform, obviously for this customer, was a win. We think it's a great bridge to help customers future-proof their build between now and whatever the standards for liquid cooling look like in the next couple of years, because it's pretty much the Wild West out there today. This gives you an option to support any hardware across any vendor at very high densities, efficiently, and at a true lower cost to deploy than the alternatives along the market today. As I promised, that's my email address. If you guys want, I certainly would be happy to send you the actual case study report with all the engineering studies from the customer, so that you can look into it and see for yourself that those were their results as published, and we just wanted to share them with you today. It's way better to see somebody else actually